Well, welcome to your first lecture of Math 065. We're starting in section 1.1, and you can see the title is Number Sets and the Structure of Algebra. So this is the lecture guide that I created to go through all of the content of this first section, leading into your first homework assignment, the section 1.1 homework assignment in My Lab Math that corresponds with this one. So you can see that we're first of all going to look at some of the vocabulary of algebra, which is really, really important for you to understand so that we are all speaking the same language. Mathematics really is its own language, and it's important that when I use words, certain words and terms, that you understand the same meaning as I understand. And that way there's no confusion. So the first word we're going to look at is the word variable. And a variable is a symbol that can vary in value. That's why it's called variable. So vary means that it could change. So you could have the variable x, for instance, that can represent 2 in one situation, but in a different context, x could represent the number, let's say, -17 or some other value. So any letter can be used as a variable. We tend to use lowercase letters for variables, but not always. And so that's variable. Now, a constant is actually the opposite of a variable because a constant is a symbol that does not vary in its value. It always stays the same. So all the real numbers in the world, like 1 and 5 and 2/3 and -17.2, like you see here, these are all constants because their values don't change. 1 is 1 is 1. It doesn't change to something else. We also have some constants that are irrational. And that means that, and we're going to talk about the definition of irrational later in this lecture guide, but basically it means that there's infinitely many digits in the number, and they don't repeat any sequence of digits, and so therefore we can't write those numbers out and write all those infinitely many digits out. We just don't live long enough. So we can use a name or a symbol for that. So little e and pi are names of constants that are irrational, that it's just easier for us to call them by one of these names rather than trying to write out this ridiculous number of digits. And so there's the first couple of definitions for you. Now in algebra, variables and constants are used to make up expressions, equations, and inequalities. We're going to look at each one of these later on in this course, right? But for now, we need to make sure that we understand all of the values of that variables and constants can be, and those are the different sets of numbers. So let's talk about the definition of a set next, right? So a set is a collection of objects or a collection of numbers. And to write a set, we typically use these set braces or set brackets that you see here. Separate, and then we individually list out the elements of the set with commas in between each element. And so if you think about the word algebra, in example 1, we're going to write the set that contains the letters of this word. Now keep in mind that once an element is in the set, it's in there. So you don't need to make duplicate entries of that same element into the same set. So when I write the set, whoops, that was a sloppy symbol there. Let's give it another go here. There we go, that's better. The word algebra has an A in it. It has an L in it. It has a G in it. It has an E, a B, an R, and you'll see that it has another A in it, but A is already listed as an element to my set. And once it's in there, it's in there. I don't need to make any duplications, and in fact, I should not duplicate any elements in a set. And so all I have to do now is close that set brace or that set bracket. And so that's how we do that. But more commonly, the sets that we're going to be dealing with in all of mathematics are numbers, right? So numbers can be classified into number sets. And on this page, and actually going into the next page, you'll see some of the sets of numbers that we're going to be dealing with in this course. In fact, all of the sets of numbers that we deal with in this course will be listed here. And that doesn't mean that that's all of the sets of numbers that there are in the world. It's just all the ones that we're going to deal with in this course. So the first set of numbers is called the set of natural numbers. And you can think about the set of natural numbers as the set of counting numbers. So when a small child learns how to first count something, what number do they begin with? They begin with 1, and then they move on to 2 and 3 and 4, and so on and so forth. So that's what natural numbers are. They're actually the counting numbers. The set of whole numbers are actually a set that has all of the natural numbers in it, but it also has the 0 in it. So it's the set of natural numbers plus a 0. And so this is your set of whole numbers here. So your natural numbers start at 1 and count up by 1, and your whole numbers start at 0 and count up by 1. Okay? The next set of numbers that we're going to deal with is the set of integers. Now you'll notice that all of these numbers that are whole numbers, the 0, 1, 2, 3, 4, and on and on and on, adding 1 each time, are a part of the set of integers. Here's the 0, 1, 2, 3, then there would be 4, 5, 6, and so on and so forth, going up by 1. But you'll notice that they're also going down by 1. So it's actually the set of whole numbers and their opposites, right? So this is what your set of whole numbers consists of. Or sorry, integers consists of. And so now we're going to move on to the set of rational numbers. Okay. Now rational numbers are any numbers that can be expressed as a fraction. They can be written in the form of a fraction. Now that doesn't mean that they have to be written in the form of a fraction. They don't have to look like a fraction, but they have to be able to be written as a fraction and still have that equivalent value. So if we take a look at some rational numbers can be written as fractions, things like 1/4 or 25 31sts, something like that, right? But they can also be whole numbers because, for instance, the whole number, let's say the whole number 2, right? Well, that can be written as a fraction if you think about it as 2 over 1. So that means 2 is also a rational number. In fact, any whole number, or actually, in fact, any integer, and that means the whole numbers and their opposites, can also be written as fractions. So for instance, -3 could be written as -3 over 1. That's equivalent, right? And so -3 is also a rational number because we can write it as a fraction as if we want to. All right, but what about other types of numbers? So for instance, what about something like 0.5 or 0.5 or 0.5, excuse me. Well, many of you may recognize that this is, in fact, the fraction 1/2, right? And there's a couple of ways that we can determine that. So one of the ways is to think about this in terms of place value, right? So this 5 is actually the first digit behind the decimal, and that is the 10ths position. So this is read 5/10. So we could think about this as 5/10. And then in our next section, in section 1.2, we're going to talk about how we could simplify a fraction like 5/10 by dividing out any factors that the top and the bottom, the numerator and the denominator, have in common. And both top and bottom actually have a 5 in common. And so that's where that 1/2 comes from. But there is actually an easier way, and I forgot to pull up my calculator, so I'm going to do that real quick here. Give me just 1 second. So there's an easier way to determine whether a number can be written as a fraction if you're not sure that it can. So I'm going to just go ahead and type in that 0.5, and then you can either hit enter now, or you could just go right to this math menu here. And again, this is a TI-84. It is a requirement for this course. You can use either a TI-83 or a TI-84, and there's many versions of each of them. But as long as it's an 83 or an 84, it'll have what you need for this course. These calculators have a button called Math, and so I'm going to press that Math button. And the very first option here is this little arrow here, number 1, that says this arrow fraction. This means you want to change something to a fraction. So it's already highlighted. I could either press the digit 1 or I could press enter because it is already highlighted. So I'm just going to press enter. And that chooses the option. And then I have to press enter one more time to execute the command. And you can see that 0.5 or 5/10 is really just 1/2. And so that is what we can use our calculator to do. So let's take a look at a couple of other numbers and see if they could actually be written as fractions as well. 0.75, right? So 75/100ths. And you can either go through the process of changing that decimal to a fraction form here and then simplifying it, or you can use that graphing calculator and you can type in 0.75, go to the math menu, choose number 1, and then execute the command by pressing enter. And you can see that that can be indeed written as 3/4. Okay. Oops. And so if you are trying to determine whether something is a decimal and you want to see whether it can be written as a fraction, and therefore that would make it rational, you want to know whether decimal has digits that either terminate or repeat, because those are the ones that are going to be rational. Those are the ones that can be written as fractions. So for instance, if I have something like 0.3 with the bar over the top, right? Can that be written as a fraction? Well, let's go to our calculator, and I can't put that little bar over the 3, but what I can do is mimic what that means here on my screen by just typing in a whole bunch of 3s, like as many as I can fit, and you can see I can't fit anymore. It'll keep letting me type, but you can see it's kind of off the screen already. So I'm just going to go right to my math menu, and I'm going to choose choice number 1. I'm going to change it to a fraction, and you can see that that is actually 1/3. So that means that all of these numbers, 1/4, 25 31st, whole numbers or integers like 2 and -3, decimals like 0.5, 0.75, and 0.3 with the bar over the top, that are either terminating decimals like these two where the decimals come to an end, they terminate, the digits behind the decimal terminate, or where the digits behind the decimal repeat. These are all numbers that can be written as a fraction, and that makes them rational. But not every number is rational. Some numbers cannot be written as fractions, and so they get a different name. So if they're not rational, well, then they are irrational. Okay, so an irrational number is any number that is not rational. So how do we know what those are? Well, those are numbers that we cannot write as a fraction. Okay, so I'm going to write here, cannot be written as a fraction. Okay, if you're looking at them in their decimal formats, the decimals will have digits that digits behind the decimal that do not terminate, but they also do not repeat. But you know, you can't see all the digits forever on your calculator screen because it can only fit so many digits on a keyboard, right? On its view screen. And so what you really want to do is take the numbers that you're checking to see if they're rational or irrational and use that change it to a fraction feature on your graphing calculator. If it works, if it can change them to fractions, so you have that a over b or numerator over denominator appearance, then it's rational. But if it gives you a decimal value back, then it's an irrational number that cannot be written as a fraction. Okay, so let's take a number like the square root of 2, right? And let's use our calculator to determine what kind of a number that is. So the square root symbol is actually right above this button here in this first column that says x squared. Right above it is that square root symbol. And it is color-coded to match my second button, which is like a shift. So you press the second button first, and then you go down and you press the x squared button, and you get that lovely square root symbol, that radical. So I'm going to put that 2 inside of there, and I'm going to just show you what the value of that is right now. So all I did is I pressed enter, okay? And, okay, so it doesn't look like anything's repeating, but I can't tell if it's terminating, like 2, really the last digit down over here, or are there more digits behind that 2 maybe that simply won't fit on the view screen because there's only so many digits that you can fit on this view screen. It's not infinitely large. There's you know, it's bound by the size of the view screen. So what I can do is I take that value and I can go to my math menu and I can use that change it to a fraction feature, execute the command, and you can see it gave me that exact decimal value back again. It was unable to give me a fraction like it was able to give me earlier for the ones that were rational. Now, because it could not change it to a fraction, I now know that that square root of 2 number is actually an irrational number, okay? Actually, anytime you try to take a square root of a number that's not a perfect square, or a cube root of a number that's not a perfect cube, or a fourth root of a number that's not a perfect fourth power, and we're going to talk about all of those things in this course later on, those are always going to be irrational numbers, okay? But if I try to take the square root of a perfect square number, like the square root of, oh, let's just say 9, right? What I get is a lovely whole number, the number 3. And I know that any whole number can be written as a fraction by just putting a 1 underneath it, right? 3 over 1, or 3 divided by 1 is 3. So this square root of 9 is rational. Square root of 2 was not rational, okay? So now I'm hoping that we understand that things like the square root of 2, the square root of 3, the cube root of 7, and numbers like pi and little e, all are on your calculator as well. So the pi button is right above, so if you find your clear button on the right-hand side, underneath that is this sort of upward-facing arrow. It's called a caret, and it is designed to put things into a superscript position or an exponent position. But you'll notice not that, but right above it is the little symbol for pi that is color-coded with my second button. So I'm going to press second and that caret, and you're going to see that pi symbol come on the screen. Now, if I hit enter, this is its approximate decimal value, right? But is this terminating, is it repeating, or is it neither of those? If it's terminating or if it's repeating, then it ought to be able to be written as a fraction, and that makes it rational. But if it's not terminating, if it doesn't really end here at the 4, but if more digits are behind it, and if there are no repetition of any sequence of digits, right, then that makes it irrational, and my calculator will not be able to change it to a fraction. So let's test it out. Let's go into the math menu. Let's change that to a fraction. And you know what? It couldn't. So pi is another example of a number that is irrational, a number that cannot be written as a fraction. Okay? Now, we understand that some numbers are rational, and if they're not rational, then they have to be irrational. So it's one or the other. There's no overlap between those two. But if you put the two sets of numbers together, and that's called a union, putting them together, what you get is actually the set of real numbers. And the set of real numbers is actually the largest set of numbers that we will deal with in this course. That's not all the numbers that there are. There are sets of imaginary numbers and complex numbers, and so there's more sets of numbers than just the set of real numbers, but that is the largest set of numbers that we are going to deal with in this course. So, whoops, I did not mean to do that. Okay. So I have this little think about box here that says, now that you have the definitions for each set of numbers, fill in each box in the graphic organizer below with the names of each number set. And think about which sets are subsets of other sets. Okay, so now if I scroll up a little bit further, and normally had we been in a classroom, I would have had you talking about this in small groups with your fellow students, and you guys could come up with this on your own. We're not in that situation, unfortunately, so I'm just going to lead us through this. But if you'd like to try on your own, simply pause this video right now and give it a go on your own. Okay, and you can see that there are boxes that are inside of other boxes. This one is actually inside of this one. Okay, and this one is actually inside of this one, and this one is actually inside of this one. But this over here is completely separate from everything on this side. But the left side and the right side are put together to form one big set. And that one big set is the set of real numbers. So I'm going to label that first. The set of real numbers is the set that joins together these two sets. Now, what are these two sets? Well, they are the sets of rational numbers and if numbers are not rational, then they are irrational. So irrational numbers have to go over here. So remember, rational numbers are basically numbers that are fractions, or they can be written as fractions. So they will include numbers like 1/2, but they will also include numbers like -4, because you can always put a 1 underneath a -4. And they will also include numbers that have terminating decimals like 0.7, or numbers that have repeating decimals like 0.73 with the bar over the top of both of those, right? So numbers that have either terminating decimals, 7 is the last digit here, or repeating decimals, right, like this, those can be written as fractions as well. And remember that irrational numbers cannot be written as fractions. Okay. Now, inside of the rational numbers, we have those other three sets that we talked about on the previous page. So we have our set of natural numbers, whole numbers, and integers. And I want you to see that if you just look at these four sets together right here, right? The natural numbers are just 1, 2, 3, 4, but the whole numbers are all of those with the 0. So this set is actually inside of this set. So I'm going to kind of show that by using a little arrow. So all of these are, all of the natural numbers are inside of the whole numbers. Now look at the whole numbers, right? 0, 1, 2, 3, 4, and so on. Those are all in the integers, plus their opposites are here as well, but these are a subset of these. So all of the whole numbers are inside of all of the integers, right? And remember that the integers are actually numbers like 2 and -3, and they can be written as fractions if you put a 1 underneath them. So all of these numbers that are integers are actually a subset of the rational numbers, because all of the integers can be written as a fraction. Now, that's not all of the rational numbers, but that's some of the rational numbers. But all of these are in here as well. So if I go back to that table, that graphic organizer that I have set up here, let me go back to my original color here, right? The smallest set of numbers here is actually the set of natural numbers. Sorry, it's a little sloppy writing on my screen. But the natural numbers are a subset of the whole numbers. The whole numbers are a subset of the integers. And the integers are a subset of the rational numbers. And the rational numbers are a subset of the real numbers. The irrational numbers are the only ones that are separate, but they are part of the real numbers. So let me just complete this by just reminding you that this is your counting numbers. This is starting from 0 and then counting on up by ones. And these are your negative, or in other words, the opposites of your whole numbers and your whole numbers. So it's kind of like the positive and negative whole numbers, okay? So remember that numbers that cannot be written as fractions, that are irrational, those are numbers like pi, or Euler's constant, little e, or the square root of 2, or the square root of 7, things like that, that you can't change to a fraction on your graphing calculator, okay? So hopefully it's going to get you through the majority of the homework that you're going to have to do for this section, but I thought we'd go through just a few more examples to make sure that you're really understanding the concept of these number sets. So to which number sets, and notice the S on the end of sets here, does the number 3 belong, right? Well, if a little kid was counting the number of cookies on a plate, for instance, would they ever reach the number 3? Is that a counting number? Well, yeah, it is. 1, 2, 3, right? So it's definitely a natural number, okay? And natural numbers are also whole numbers. And whole numbers are also integers. And all integers are rational. And all rational numbers are also real numbers. So if I go back to that chart one more time, the 3, the smallest set it's in is the natural numbers. But that's also in the whole numbers, it's also in the integers, it's also in the rational numbers, and it's also in the real numbers. But it is not an irrational number, because 3 can be written as a fraction just by putting a 1 underneath it. Okay? Okay, so which ones of these are rational and which are irrational? So hopefully you realize that 2 is indeed rational. And we know that it's rational because we can write 2 as 2 over 1. So I can write it as a fraction. And remember, that's what rational means. Rational means that it is a number that can be written as a fraction. Well, in B, we have 3/7, and that already is a fraction. So, of course, that is also rational. Okay. Pi. Well, remember my use of the graphing calculator to check and see if pi could be written as a fraction. So it was not able to be written as a fraction. So I'm going to write that this is irrational. And my reason is going to be that it cannot be written as a fraction. Okay? Whereas 2 could be written as a fraction. And B here, the 3/7, this is already a fraction. It's already written as a fraction, right? What about this one? 0.3, or in other words, 3/10. Well, actually, just the way I read it right there as 3/10 tells me that this can indeed be written as a fraction. And that means that it is indeed rational. And you can use your calculator to do that change. And the same with this one here. So 4.3, where the 3 has a bar over the top, that means there's repeating going on. Now remember, in the definition of rational numbers, we know that rational numbers are numbers that can be written as a fraction. But one of the things that I also said in that definition is that if they are written in decimal form, there will be either a repeating digit or sequence of digits behind the decimal, or there will be a terminating digit behind the decimal where it absolutely ends. This one is repeating, and that tells me right away that it is indeed rational. But if you are not sold on that idea, you can definitely pull up your calculator and type in 4 point and then do just a whole bunch of 3s. And then just use your math menu, change it to a fraction, and see if it does. And you can see that it did. It's giving me 13/3. So I'm going to write that this is equal to 13/3, and that makes it rational because it can be written as a fraction, right? Part F is the number -7. Well, -7 is an integer, and any natural number, whole number, or integer can be written as a fraction simply by putting a denominator of 1 underneath, and that makes it rational. Whoops, rational. There we go. And just 2 left here. Square root of 2, that's actually one that we did on our graphing calculator. This one is definitely irrational. And that's because it cannot be written as a fraction. And how about 0? Well, remember, 0 is not a natural number, but it is a whole number and it is an integer, and that means that we can always give it a denominator of 1, and that means it can be written as a fraction, and that means that it meets the definition of a rational number. Okay, so that is all with the sets of numbers that we're going to deal with in this course. There's just a couple of minor little topics that I also want to remind you guys about here. So I'm going to take a look at a few more examples. One of them is the ability to graph a number on a number line in the correct position. And so remember that any time that you are graphing a number on a number line, okay, numbers are smaller to the left and larger to the right. Okay, so for instance, if I put 0 right in the middle here, numbers to the right, this is where 1 and 2 and 3 and 4 will go, and so on and so forth. and your negative numbers counting down will be on that left-hand side of 0. Now, where would positive 2 3/4 be? Well, positive 2 is right here, but it's 2 3/4, meaning 2 plus 3 out of 4 more, right? So what I have to do is I have to go out to where the 2 is, and I'm going to change colors here real quick, and I need to take this space that's past the 2, so this space between the 2 and the 3, and I need to divide this space up into 4 equal parts. So the denominator is the number of equal parts that you divide it up into. And so I'm going to just put in a couple little tick marks here. There, you can see them. So there's 1 space, 2 spaces, 3 spaces, 4 spaces here. So this increment, so this unit from positive 2 to positive 3 is divided up into 4 chunks. But I need 3 of those equal parts. So it's the number of parts that I'm going to take that is up on the top. And so I need 1 part, 2 parts, 3 parts. This one right here, this is where 2 3/4 is located. Okay? All right, let's do that one more time. This time I'm giving you a number that is in a decimal format. But once again, your positive numbers are to the right of 0, and your negative numbers are to the left of 0. That wasn't meant to be a bar, that's just a 3. So I'd have -1, -2, -3, and so on and so forth. So this is -1 and 78/100ths, right? So -1 means I'm moving from 0 to -1, but then I need 78/100ths more of the distance from -1 to -2. So I'm not going to, so this is equivalent to -1 and 78/100ths. And there is not any chance at all that I am going to take the space between -1 and -2 and divide it into 100 equal sized spaces. No way. But if I'm going to go 78 of them, 78 is more than half of 100. Half of 100 is 50, right? So this is where -1 and 50/100ths would be, right? Smack dab in the center between the -2 and the -1. So 78 has to be even closer to the -2. So it's going to be down in this region here. So I am going to do a little label, sort of approximating and labeling it right here. That's where this -1 and 78/100ths is going to be located. And that's an approximate position because I'm not dividing that space into 100 equal parts. So just wanted to remind you guys of the fact that on a number line, smaller numbers go off to the left and larger numbers go off to the right. Okay, so the smaller a number it is, the further to the left it is. The larger a number it is, the further to the right it is. So that's an important concept when you're dealing with another mathematical operation, an idea that is called absolute value. So the absolute value of a number is defined to be its distance from 0 on a number line. So every absolute value of a number is either positive or 0. And that's because distances can't be negative. I mean, think about it. Have you ever walked a negative number of miles or driven a negative number of miles, right? It's just not possible. Distances are positive measurements, or 0, because you can walk 0 miles or drive 0 miles, right? But you cannot travel a negative distance. So anytime you see these brackets, and remember, absolute value will have some number inside, and then it will have these brackets. these vertical bar brackets on either side of your number or variable or expression, those are what tell you that we want the absolute value of that number. So the absolute value of 2 is the distance that 2 is away from 0 on a number line. So here's 2. From 0, it is 1, 2 units. So this distance is 2 units away from 0. So the answer here is just 2. Using the exact same reasoning in this second question, it's asking for the absolute value of negative 4.5. Right? So here's 0, negative 1, negative 2, negative 3, negative 4, negative 5. So negative 4.5 is going to be right there. How far away is that from 0 on the number line? In other words, what is this distance? How far would you have to travel to get from 0 to here? Well, you would have to travel 4.5 units. So once again, the absolute value of a number can never be negative. It must always be positive. And that's because it is defined to be a distance. And distances must be non-negative. They could be 0 or they could be positive, but they cannot be negative. And that gives us enough information to tackle the last example here, which is deciding whether a number is larger, smaller, or equal to a second number. So we're going to just choose the right symbol to place in between in this box here. So is 4 less than, equal comes first. Is 4 equal to negative 4? No. Because if you think about it, remember, on a number line, here's your 0. 4 would be out this way, negative 4 would be out to the left. So anything that's further to the right is bigger. Anything that's further to the left is smaller. So negative 4 is actually smaller than 4. In other words, 4 is actually bigger than negative 4. So we're reading this from left to right, so we have to say 4 is what than negative 4? 4 is greater than negative 4. This is that greater than symbol. The greater than symbol always opens up to the larger number. Okay? It's like the Pac-Man wants to eat the bigger amount of whatever. Okay? Or alligator, however you want to think about it. So if we look at the next one, 0, negative 1, negative 2, negative 3. Okay, negative 2.5 would be here, negative 2.7 would be even further down to the left. So if negative 2.7 is further to the left than negative 2.5 is, then negative 2.7 is actually smaller than negative 2.5. So negative 2.5 is larger. So you have to use a less than symbol here. Okay? And just 2 more left, and then we're finished with this lecture guide. So this one, you'll notice, has absolute value brackets in place, which means we need to figure out what this means first before we can actually answer the question. So what is the absolute value of negative 3 and 5/6? Well, it's just 3 and 5/6. That's its distance from 0. So we'll put that box back in between. And this is what the problem becomes. If you look at the number on the left and the number on the right, they are identical, so these two are equal. And then we have another absolute value right here, so we have to figure out what is that one, right? So the absolute value of negative 7/10 or negative 0.7 is positive 0.7. So it's really saying, is 0.7 equal to, greater than, or less than negative 1.5. Anything that's positive is always larger than something that is negative. So this one has to be larger, and that's our answer for this one. So hopefully this is going to give you a nice foundation to build on, because everything we do in this course is going to build on prior knowledge. So anything we do in the next section is going to be dependent on how well you learn this content. And it's going to snowball that way all the way through the course. So think about it as stairs. We just built the bottom step, but we need to get to the top of a high tower. So you've got to have a really strong first step. Otherwise, when you step on it, it's going to collapse. So you're building your mathematics knowledge step by step by step. And every step matters because you don't want to crash through, right? So build each step strongly. Make sure you're really understanding. If you're not understanding, please reach out to me, attend my office hours, send me an email, send me the Ask My Instructor option from homework. Do whatever it takes, but please, please, please make sure that each step of your foundation is strong. All right, and remember, you are not alone. I am here, just not in person. Okay, so good luck, and we'll be talking soon.